So 12.1 is inference for regression. Oh boy, regression. Remember when we were doing regression back in chapter 3, right? We would build a scatter plot, put our explanatory and our response variables. We would plot the graph, and we would eventually create a regression line. So what we are going to be doing is inference, which means like basically running a test or doing confidence intervals on some component of the regression line. All right. So that's what we got going here. That's what we're going to reintroduce ourselves back to chapter 3, regression, which means we are looking at bivariant data. Two variables. One is going to be the explanatory variable. The other one is going to be the response variable. Remember when we did this? All right, let's jump into it. Here we go. 12.1, let's talk about a little ideas of regression. So a sample regression line. So I take a sample, I plot it on the scatter plot, I build the least squares regression line, so least squares regression line. Remember, that's what we're building. And this is how we would write it. We would write it y hat equals a plus bx, where this is my predicted y value. This is the y-intercept. And this b right here is the slope of that regression line, right? So this is what we did, and then we'd use that. We'd make predictions, we'd find residuals, we'd do things like that, right? So that's what it is. So here's what we want to do is now, what is the true regression line? Well, the true regression line, this is the actual factual regression line. Remember, this came from a sample. This is the true population regression line, okay? So here's what we would write it for a true population regression line. We write y without the hat equals some alpha value, so a Greek symbol alpha representing the A, plus some beta value representing the B, x. So what does this actually mean? This is the actual y value. This is the, oops, let's do this. I don't know why I'm mixing up my colors here. So let's call that actual y value. And then this one here, there is the true y-intercept. So notice how we're using a Greek symbol again. Remember, Greek symbols always represent the population. And then here's the true slope. Now, are we actually going to be able to know the true regression line, this true regression line? Probably not, right? That's why we do stats, is we take what we get out of our sample and we hope that it points us to what is true in there, okay? So what we are going to focus on, really, we could focus on any of these aspects, but in our level of stats, we are going to focus on the predicted slope versus the true slope. So I'm going to use this predicted slope to try to give me a good idea of where the actual true slope is, because slope of a regression line is very important. Tells us if we have growth or decay, right? Are we rising or are we falling? It tells us how quickly you're rising or you're falling. Or if you ended up with a zero slope, that means there's nothing changing over time, right? So that's what we're going to be doing. So the sampling distribution of B. So imagine this. Imagine I went and took a sample from a population, and then I got its scatter plot. I calculated its slope, and let's say its slope was 3. So you know what I would do? I put a point. And then I go in there and I do another sample, and I found that its slope is 4. So I put a point. I go and do another sample, and I find that its slope is 1. So I put a point. And I do this over and 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 over again. Right? You get it, right? This is going back to the idea of what is a sampling distribution, chapter 7, first semester. Sampling distribution is all the possible samples of the same size from the same population with the character that we want. In this case, the character is the slope. And I plot them all in the same plot. Right? And this would then, the sampling distribution then would say this is what it looks like if you took all the slopes from all the possible samples and plotted them on the same graph. This is what it would look like. So here's what we need to know, though. The average of all these little b's should be right in the middle, and it should be unbiased, so it should equal the true value, the true beta value on this, right? The standard deviation, which actually in this case we call the standard error in B, is going to be equal to, here's a little formula, it's on your formula sheet. It's the overall standard deviation of the residuals divided by the standard deviation of just the x values times the square root of n minus 1. We're not going to do that calculation very often, but we should know that, right? So we call this the center. We call this the spread. And what else are we missing from our socks? We're missing the shape. Shape is important. Well, we're going to have to take on the shape. Guess what it's going to take on? It's going to take on a T distribution shape. A T distribution. What does a T distribution looks like? It kind of looks kind of normal, but it's got some error involved in it. So we will want to take that into account. So it's a T distribution, but here let's add this. It's not only just a T distribution, it's got its own degree of freedom. And since it is a bivariant data, our degree of freedom is going to be n minus 2. Oh, that's a little bit different than what we've been doing. Like when we did a T distribution for means, we would do n minus 1. Since it's bivariant, I need to be able to spell that right. Bivariant data. So the word bi means 2. So when we're doing our degree of freedom, just make sure you subtract 2 instead of 1, like we used to. Okay, so that's going to be the idea. That's going to be the setup. So this is going to help us just to think about what is going on in this distribution. Okay, so let's talk about conditions. So we call this our assumption checks or our conditions when we go to and do these things. So whether we're doing panic or phantoms. So let me just kind of write these out instead of actually going through each one. But linear, the scatter plot needs to show a linear relationship. Also, the residual plot does not have any curved patterns, right? So we're going to get in the habit of sketching each of these. So literally, we're either going to look at a data set or have it. So let's just say I looked at the data set and it looked very much normal, right? In the actual scatter plot. So you're literally going to have to use your eyes and see. And we're going to be like, okay, that looks very much normal. Another thing you can do is you can look at the residual plot. So remember this from chapter 3. If we look at the residual plot and we don't see a pattern, right? That's the most important thing. I do not want to see a pattern involved in this at all, okay? So if you see a pattern, linear is no good. No pattern is good. Okay, no pattern in my residual plot. So those two will kind of help check for linearity. All right, independent. How do we usually solve independent? We call that the 10% rule typically. So just get in the habit of doing 10% rule. Oh, and down here, random. How do we check random? I'm looking for the words random. So you should be pretty familiar with independence and random by now. So it's these other three. Okay, so then number 3, it says a normal distribution, or really a T distribution. It cannot show any strong skewness, right? But we are talking about the residuals. So literally what we'd want to do, we'd want to look at the residuals, and I want to make sure that they are following some kind of normal pattern. So typically what you do is you extract them and you put the residuals onto a plot themselves. And what we're hoping to see is them stack up in kind of a normal-ish style t-distribution pattern, right? That's what I want my residuals to look like. If we have the ability to, we're going to draw the curve and we're going to do it. And I'm going to tell you from the get-go, you're not going to be drawing too many curves because a lot of times they're just going to give them to us. And then let's look at the fourth. So there's 4 qualifiers on these conditions where we used to only be doing 3 qualifiers, right? So equal standard deviation. The residual plot does not show a clear sideways Christmas tree pattern, right? So that is looking at the residual plot again. What we don't want to see is this. I like that sideways Christmas tree pattern, right? It doesn't look like this, right? That's a sideways Christmas tree. Or, so we don't want that happening in our residual plot, or we don't want it reversing, right? Where it kind of looks like this. I don't want to see that. And that'd be no good, okay? So just look at your residual plot and make sure that there's no funky standard deviation thing happening here, right? So that's what that is all about. Okay, so there you go on that one. Standard error of the slope. We've already talked about this, but just to have that formula, it's actually on your formula sheet as well. Standard error of your slope is equal to standard deviation of the least squares regression line divided by the standard deviation of only the x values times this. And a lot of times we're going to find this, we're going to have this given to us. If not, we can do a calculation, but it is very rare that we need to actually do this calculation. All right, let's keep moving on. All right, we're going to be doing 2 things. We're either going to be doing an interval or a test, right? So, are you saying panic or are you saying phantoms? Okay, so we just need to fill in the pieces. So what does the actual interval for slope look like? That's going to be the kind of the next key that we're looking for on this. Since we are using the slope from the sample, that becomes our point estimate. Plus or minus, since we're doing a t distribution, I'm going to go look up a t critical value. We should know how to do that by now. But remember, I'm going to just go and write it here too, that your degree of freedom is n minus 2 now and not n minus 1 like it used to be, times the standard error of the slopes, right? So it looks the same as it used to be, and that will create our interval. As long as we do the assumption checks, we show this, calculate it, we are 95% confident that the true slope is somewhere between here and here, right? So there we go. Let's talk t-test for slope on this one, right? So if I'm running a t-test for slope, there's a couple things I'm going to want to make sure I know. I know that my null hypothesis, right? It's going to be a standard. It is going to be that the beta, in this case right now, unless otherwise stated, we're going to always have a standard null hypothesis equal to 0, right? That's going to be usually the claim, because what does that mean? That means there is no association between the x and y, right? No association between them, because if you have a 0 slope, think about that. I know I'm going off on a tangent here. But if I have a data set, like it's just all over the place and I'm trying to figure out what is that association with my x value and my y value, and I throw a least squares regression line and it looks like that, that's no predictability. That means any value I choose for x, I get the same value of y. Well, that doesn't help me in making predictions for future, right? So we call that a no association. So if we are looking for that, that's what that would be. Alternatively, we are going to say the true slope beta is greater than 0 or maybe less than 0 or just straight up not equal to 0, right? So that's going to be the one. Now, there are some instances, we're not going to get into it as much, where you might change the slope and we're going to test, is the slope actually 1? Is the slope actually -5? right? Whatever the slope might be, we can always test that number, but we are going to have a standard where we're usually going to be talking about just no association here. So that's what's going on in that. Okay, so then you would run the test with the assumptions again, right? Those are those 5 things that we claimed above. And then at some point, we would need to run the actual t distribution, right? And remember, if I'm going to draw the curve, shade the curve, since most of the time our beta is going to be equal to 0, we're going to set this thing over 0, and we're going to actually calculate our t-value. So here's what you might want to write down. T-value is going to be my sample slope minus the claimed slope, which is usually going to be 0, right? So I'm just going to put that. That's probably going to be 0 most of the time, over the standard error of b. And then we go look up a p-value based on a degree of freedom n minus 2. All right, so that's what it looks like right there. All right, let us figure out how to do this stuff on the most common output that you're going to get. Most of the time, you're going to get computer output. If you remember this, we used some of this way back in chapter 3. And we used to say, I ignore, 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 and only look at this number, this number, this number, and this number. That's all we were doing back in chapter 3. Well, right now we're gonna stop that, and we're gonna come back and we're gonna look at some things. I am still gonna suggest that you ignore the adjusted r squared value. Do not want that ever. Okay? Don't want it. Don't want it at all. But what we do want are some of these other numbers. So let's talk again about what these different things we have. Okay, so first listed, the word constant. This row of stuff is all for the y-intercept. So all of this belongs to the y-intercept. Matter of fact, the coefficient itself, this is the y-intercept itself. The other stuff is all stuff that belongs to the y-intercept. Then whatever the descriptive word is, drop height in centimeters, that entire row belongs to the slope. That's all stuff that belongs to the slope. Matter of fact, the coefficient listed is the actual slope, right? So that's what we need to know. So then when you see the word SC coefficient, there's the standard error of the intercept. Here's the standard error of the slope. Wait, time out. Did you just say standard error of the slope? Well, it's going to be that value. So a lot of times it's going to be given to us, right? We're going to have the nice idea of what that is. Also, as I keep going, here's the t-value for the intercept. Here's the t-value for the slope. Wait, time out. Did you just say t-value for the slope? Did you just tell me what that is right there? Yeah, we did. Okay, so yes. And then what else do we have? We have the p-value for the y-intercept and the p-value for the slope. Timeout. Did you just say that this is the p-value? So when I need to go obtain a p-value, this is what I'm going to be looking for? Absolutely. Okay, so since in this round we don't really care much about the y-intercept in this level of statistics. Some other levels they do care about it. We don't right now in this level. I'm going to ignore that, and so all the other things I do want, and we're going to use that in just a second. I'm going to show you how to do that. Let's also continue to talk about, right, what is the S? This is the standard deviation of the least squares regression line, or sometimes called standard deviation of the residuals, because it's the same idea. Yeah, and that is the S that goes on the top of the standard error calculation. Okay, so that is that S if you ever needed it for whatever reason. I'm not going to make you do those. And then here's the r squared value. Remember that the r squared value has kind of a statement that goes with it. So you probably want to remember that statement. It is the percent of variation that that can be explained by the least squares regression line between x and y, the explanatory and the response variables. That is almost a straight up statement that you'll see a lot. Percent of variation between x and y that can be explained by least squares regression line. Okay, that's the R squared that's given to you in case you ever needed it. All right, let's do a couple problems and wrap this thing up. All right, example 1, here we go. So you can kind of follow along. Everyone knows that cars and trucks lose value more they are driven. Can we predict the price of a used F-150 Supercraft 4x4 if we know how many miles it has on the odometer? A random sample of 16 used of those was selected from among those listed on sale. The number of miles driven and price in dollars were recorded for each of the trucks. Here's the computer output from a least squares regression analysis of the data. Construct, interpret 90% confidence interval. So here it is, construct, interpret 90% confidence interval. All right, let's think about panic. Okay, and then it says for the slope, right? So we're going to focus on the slope and we're going to try to estimate that. Okay, so I'm thinking panic. So assumptions. There are 5 assumptions that need to happen, right? We want to think about each of those, right? I'm always going to start, I'm going to start backwards on this. I'm going to say random. So, right, is it random? A random sample. So I see that up there, random. Check. Number 2, 10% rule, right? So we'd say all F-150, I don't know, the super cab and blah, 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 blah. Is there more than 160 of those for me to choose from? Probably. I would guess so on autotrader.com. Number 3, okay, now we're getting into the specifics. So let me come back up here and I'm going to try to think about all of these things. Is it linear? Is it normal? Is it equal standard deviation, right? So based on the graphs, is it each of those? Is it linear? So really what we're going to point to for this, is it linear? I want to look at the actual graph. So I'm kind of looking at the actual graph and it looks very linear. And then go ahead and look at the residuals, make sure there is no pattern, right? So I'm going to say residual graph, no pattern. Okay, so that's because it's already shown to me up there, right? So let's just use it. All right, so is it linear? That's one of them. Another one, is it normal? The dot plot of the residuals, right? We don't want any skewness or outliers. Here it is, residual. Do you see any skewness or outliers? Nope. So we're going to say normal. No outliers or skew. All right, so that's going to take care of the normal check. And again, what am I looking at? I'm looking at the residual plot here. A lot of times you're not going to be given that, and you just say like, assume normal. And let's look at the next one, equal standard deviation. So that's looking at the residual plot, making sure we don't see a Christmas tree shape. So I'm going to go this number 5, equal standard deviation, right? No shape in residuals. Okay, and again, what am I looking at? I'm going to highlight that in green because I'm actually looking at the same plot up here. I'm looking at the residual plot. All right, there we go. Let's go to the interval calculation. Interval calculation, here we go. You ready? Let's do this. It's going to be I'm going to write it in general. B plus or minus T star times standard error of B. Okay, so let's go find, first of all, the B value. Remember, coming up here, anytime you see the constant or the word, the descriptive word, not the word constant, the descriptive word, then I'm going to take the actual B value. So right now, let's write it as negative 0.16292. So go ahead and use the actual numbers that they give you there. T star value, we're going to have to look that up in just a second, but I will come back to it. I'm going to leave a gap to come back to it. Standard error of B. Standard error of B, check it out. This number right here, because it's listed under standard error of the coefficient. The coefficient right now that we're talking about is the slope. So that is the standard error of the coefficient. So they've already done the calculation for me, 0.03096. Wow, we're just down to the t star value, right? That's what we need here. So what we need to do, we need to find our t table. So I'm going to go to my formula sheet. So if you will, go with me to the formula sheet. I'm actually, before I get all the way to the t table, let me just real quickly show you on the formula sheet. Here's the formula sheet right here. And they kind of show us some of the different pieces, right? So we kind of went over the standard error. There it is. We went over where the center would be. So we kind of did some of these things right here. So we can always talk about those if we want to, but most of the time you're going to be given the stuff that you need. But let's go back down to the t distribution. And remember that we went to the t distribution. If I'm doing a z critical value lookup, I'm looking at the infinity. If I'm doing a t, I got to look up the line of the degree of freedom. So one thing I'm going to have to do on this problem set is come back to it and figure out what is my degree of freedom. So they said they took a sample of 16. So what's my degree of freedom? Degree of freedom is equal to n minus 2. So it looks like we're going to have a 14 degree of freedom. We want to do a 90% confidence interval. So let's put that all together. Here we go. 14, 90%. 14 is here. And then I'm going to slide across until I'm above the 90%. Where the crossing is, that is my number. 1.761. Let's plug it in. 1.761. All right, and we are about ready to go. Now, unfortunately, in your calculator, it does not allow us to do a confidence interval if you're not given the actual data. So since I'm not given the actual data, I am going to have to do this one by hand. So here's what I'm going to do. Negative 0.16292, and I'm using all the values they give me, plus, in my calculator, 1.761 times 0.03096, enter. That, because I used the plus sign, it gave me the upper bound. So I'm going to go negative 0.108. Let's go 399. Okay. And then I'm going to go right back and do it. I'm going to go second entry in my calculator. I'm going to change the plus sign to a minus sign. And I'm going to get the lower bound. Negative 0.21744. Okay, so there it is. I want you to notice that both signs are negative. So that means I am pretty confident that my entire slope is negative and not zero, right? It does not cross the zero. So that's just things to think about. All right, here we go. We are 90% confident. The interval negative 0.22 to negative 0.11 captures the true slope between price and miles driven. Okay, there it is. You got an entire panicked problem. So I know this gets a little loathsome, right? That we have to check 5 checks now instead of just the normal 3 that we used to. But the idea is it's always there. And a lot of times they're just going to give us the stuff to do it with. Matter of fact, that's what we're going to focus on because that's like an AP classic that they do. They hardly ever give us data sets anymore. And then just get right into your calculations. You're going to have to do that by hand if you don't have a data set, and then your conclusion always sounds the same. All right, here we go. Let's do a second example. Let's do a phantoms problem. So on a phantoms problem, I'm still thinking all those different things that we need. But check this question out. Infants who cry usually more easily is stimulated than others. This may be a sign of higher IQ. Child development research explored the relationship between crying of infants 4 to 10 years old and their later IQ test scores. A snap of rubber band on these records the crying of 38 infants. They measure the crying intensity and measure peaks in the most active 20 seconds. They later measure the children's IQ at the age 3 years using a Stanford Binet IQ test. All right. So there you go. How's the computer? Here's the computer output. So they're giving us computer output again. For the least squares regression analysis, do these data provide? All right, here we go. Do these data provide convincing evidence? Okay, phantoms. So we got to think about all the different pieces. At the alpha 5% level of a positive. So what do they want? They want to see a positive linear relationship between counts of crying peaks. Positive. I'm just trying to get that down between counts. Assume conditions have been. Whoa, time out. This is music to my ears. Assume conditions have been met. What does that mean? That means I don't have to figure out the assumption checks. Those 5 different checks, they are saying they did it for you. So don't worry about it. All right, let's hit this thing off. Phantoms. Let's go with the hypotheses. The hypotheses, we are always going to have a standard right now. Beta equals 0. That's your standard. Write it out. Beta, positive linear relationship. We want the slope to be greater than 0, positive. All right, there we go. Don't worry about the assumption checks. Let's get right into the T. All right, the T is going to be a T-curve distribution, thinking about all the different slopes that are available. And we're always going to put the claim in the center of our graph. All right, so then let's go find our B value. Okay, our actual slope value that we got from the sample is over here, 1.4929. And since we are shading greater than, we're going to shade above. Well, that was easy. All right, let's do the T. T equals my slope, 1.4929, minus the claim slope, which is 0. Right, there's the claim right up here, divided by standard error of B. Standard error of B, that's that number right there. That's 0.4870. And then I'm going to calculate this. If you want to calculate it in your calculator, you can. Otherwise, I know it's going to be 3.07. How do I know it's going to be 3.07? Because right here, they say the T value should be 3.07. Let's verify, though. 1.4929 divided by 0.4870. Oh, 3.07. It is, if I round it. Okay, so I just showed my T value. And then let's obtain a p-value. Obtain a p-value? Okay, let me do this. Check this out. P-value up here in this says your p should be 0.004. So we got our p-value, right? That's it right there. If you needed to, remember what your degree of freedom is. Your degree of freedom is always the sample size, in this case 38. Minus 2, so our degree of freedom would be 36 if we needed that to look up values and things like that. Okay, so here we have it, right? It is giving us the p-value that we need off of this thing right now. Now, here's something that you do need to know about the p-value that is given here. It would assume that they put in the correct null hypothesis, or the correct alternative hypothesis. So we would assume that since that is what they were looking for, that is the p-value they gave us. Now, if you don't have any null hypothesis, typically this value is a not equals to value, which is a doubled value, which means we take half of it for one-sided. But if they don't tell you otherwise, always assume that the p-value is the p-value that we need, and we're going to use it right there for that. So now let's make a decision on this thing. At the 5% level, that's well below 5%, so we know we're going to reject the null hypothesis. And then on our summary, let's just say what it is that we believe. We believe there is, so we have evidence to suggest this, a positive linear relationship, right? So we would say we have evidence to suggest a positive linear relationship between count of peak crying and IQ in the future. So there you have it, and we're going to use a lot of these printouts. So I want you to know your printouts, okay? So again, I would just, if this stuff all gets too confusing for you, we won't use most of this stuff here. Now we might use this and this, so we might use the y-intercept and the slope to create the least squares regression line, y equals a plus bx, right, by plugging in the right values. We might use r-squared to talk about the percent of variation that's explained. We might use this just to talk about the standard deviation of the residuals, which also tells you how much off you should be every time you make a prediction. And of course, we will be using all the stuff in the slope line. All right, there you go. We'll talk more in class.